Okay, let's dive right into the source material you shared for this deep dive. We're tackling a connection that's, well, fundamental to being human, something you probably engage with hundreds of times a day without a second thought.
That's right.
It's the link between your hands, arms, your upper limbs,
Sure.
and how you learn, how you create, how you innovate.
We've been looking over some really fascinating research, particularly a study you highlighted focusing on pencil power to production.
Right.
And this research makes a compelling case, I think, for the critical and maybe deeply undervalued role our human upper limbs play in the whole process of knowledge transfer.
So our mission today is really to unpack this research. We want to uncover how this seemingly simple physical connection,
Yeah.
brain linked to hand, acts as a kind of bridge between our internal thoughts and external actions.
Mm-hmm.
And this bridge apparently drives everything from a child's first scribbles all the way up to complex tech advancements and even national economic growth.
Yeah, the core argument from these sources is that the manual dexterity we have, thanks to evolution, isn't just a handy skill. It's absolutely foundational to turning abstract ideas into tangible results.
Tangible results in the world,
Exactly. You might look at your own hands a bit differently after this.
I bet. And this all starts, biologically speaking, deep within our nervous system, right?
Yeah.
Specifically with something called the brachial plexus.
Yes.
The research really emphasizes that human evolution put a premium on the dexterity and precision of our hands.
It really did. And this led to a much more intricate, highly developed brachial plexus in humans compared to other species.
So what exactly is the brachial plexus?
Well, it's a complex network of nerves.
Mm-hmm.
It originates from spinal nerve C5 down to T1. Basically, it's the neural highway controlling everything from your shoulders, down your arms, and right into your hands.
And it's not just about, like, lifting heavy things or throwing a ball.
Oh, far from it. I mean, yes, it handles those gross motor movements, but the source highlights that its real evolutionary advantage in humans is supporting incredibly fine motor movements.
Okay, like what?
Think about manipulating tiny objects, assembling miniature components, or performing intricate tasks with really high precision, or just getting detailed sensory feedback from your fingertips.
Right.
This advanced neural development through the brachial plexus is presented as absolutely crucial for complex tool use, for effective knowledge transfer across generations, and the very possibility of technological innovation.
The sources even draw a striking comparison here, don't they, between the arms and legs?
They do, yeah. The research points out that the human brachial plexus is significantly more developed than our lumbar plexus, which controls our legs and feet. And this difference, according to the authors, it underscores the higher precision, the control, the sort of creative potential that's uniquely enabled by our upper limbs. Capabilities that are fundamentally required in fields like science, engineering, design, where that detailed manipulation is absolutely key.
Okay, so if the brachial plexus is the biological hardware enabling this, the research identifies the starting point for this whole journey in our early years. They call it pencil power.
Yes, exactly. This is presented as the earliest, maybe the most formative expression of knowledge transfer in childhood. It's that deceptively simple act of a young child gripping and guiding a writing tool or a drawing tool.
Which, as the source makes really clear, is doing way more than just teaching handwriting.
Absolutely. The research describes this as the motor formatting of abstract knowledge. So you're taking an abstract idea, maybe the shape of a letter or a number, a simple concept, and you're using your hand, guided by your brain, to translate it into a physical, visual, spatial, and procedural form on a surface. And this physical act, it's the start of creating what the source calls brainpage.
Brainpage.
Yeah.
That sounds intriguing. Like building a page in your brain.
Exactly. Think of it as a neural blueprint, a kind of physical encoding process. When you write or sketch or draw or even manipulate tools, you're activating multiple critical brain regions all at once.
Which ones?
Areas involved in planning, like the prefrontal cortex, executing movement in the motor cortex, coordination in the cerebellum, and spatial processing in the parietal lobes. It's actively building and strengthening the neural circuits needed for planning, for complex problem solving, and for procedural thinking.
And the pencil itself. The source positions it in a really interesting way.
Yeah, it's described as motor bridge. So not just a tool for making marks, but the physical link that lets the learner convert passive cognition, an idea just sitting in the mind, into active construction and expression on the page. And this initial act, starting with pencil power, it kicks off a lifelong process of modulating knowledge through our upper limbs. It's the beginning of using physical action to process and solidify abstract thought.
This idea of using our hands to sort of modulate and process information, it doesn't just stop with childhood writing, does it? The research argues quite powerfully that our upper limbs continue to be the primary engine of innovation and dexterity throughout our lives.
They really are irreplaceable in many ways. The source points out that human upper limbs have this incredible mix of strength, flexibility, and precision. It's a blend that, well, even with all the advances in robotics, machines still struggle to fully replicate the nuance and adaptability of a skilled human hand.
All right, the source gives some specific examples where this hand-brain connection, enabled by the brachial plexus, is absolutely essential, doesn't it?
Yes, the paper highlights several key areas. In engineering, think about everything from sketching initial blueprints and handling sensitive measurement instruments
Okay,
to performing precise mechanical adjustments or maybe soldering tiny circuits.
makes sense.
Then in medical science, think about the millimeter-level accuracy needed in surgery that's impossible without highly trained fine motor control.
Absolutely.
In digital technology, it's not just the abstract code, it's the physical act of typing, using a mouse or a stylus for design, physically interfacing with complex hardware. And of course, in arts and design, it's the crafting, sculpting, painting, modeling, turning imagination into physical stuff.
So in every single one of those, it's the seamless integration of the cognitive knowledge, knowing what to do with the motor execution, knowing how to do it with your hands.
Yeah,
That's what makes it possible.
precisely. The hand is where the abstract meets the real world.
Which leads us nicely into the theoretical framework the source introduces, learnography and brainpage theory. It sounds like a call for a fundamental shift in how we even think about learning.
It really is. The theory strongly advocates moving away from perhaps overly passive learning methods and really embracing active doing. It emphasizes the absolutely critical role of motor science in the process of acquiring and transferring knowledge.
So knowledge transfer isn't just one step.
No, it posits that it's not simple. It's a phased, embodied journey. It involves neuroplasticity, the brain actually rewiring itself, motor formatting, which is that physical encoding we talked about, and then finally functional execution, actually using that knowledge to perform a task.
And the source breaks this down into, what, 7 distinct phases of learning transfer?
Right. These phases describe the journey from just initial exposure to deep, integrated understanding and application. They range from understanding definitions, they call that definition spectrum, and relationships, the function matrix,
Okay.
to problem solving, the block solver, spatial navigation of ideas, hippocampus, building complex systems, module builder, actually performing tasks, task formator, and finally developing that sort of intuitive expertise, dark knowledge.
Wow. Okay, so how do our upper limbs fit into all these phases?
Well, this is where the theory loops right back to our topic. The research emphasizes that the motor science of our upper limbs is absolutely integral to most of these phases.
7 of them.
Yes. Whether you're writing down a definition, drawing a functional diagram, assembling a physical model to understand a system, building a module as part of a bigger project, or performing a complex task, your arms and hands are the essential physical mediums. They are how knowledge becomes tangible, actionable, and deeply embedded.
So it sounds like they're saying the physical act is part of the learning itself, not just showing what you've learned afterward.
Exactly. It's not just about output. It's about input and processing through the physical action. And the source has this fascinating detail about finger mapping.
Figure mapping.
Yeah, it's the idea that the modulation of learning through the precise structured movements of our fingers and hands creates the kind of robust structural memory needed specifically for building technology and executing productive work. Your hands are active participants in actually encoding the knowledge structure itself.
That bridges the gap beautifully, then, between individual learning and the wider world of industry and economic growth. The goal shifts from just absorbing information to converting that knowledge into, well, demonstrable skill and tangible output.
And according to the source, this is where the upper limbs take on their crucial production role. Think about the environments where real-world skills are built and applied. Vocational training workshops, engineering labs, robotics clubs, digital fabrication spaces.
Right, all hands-on places.
Exactly. All of these rely heavily on applying knowledge by physically interacting with tools, machines, interfaces, using your hands to make things happen. This practical, motor-engaged application forms the absolute backbone of a functional knowledge economy.
So, the popular idea of learning by doing is, at its root, really about this fundamental motor engagement.
The research strongly supports that view. It highlights that countries or regions that intentionally emphasize motor learning techniques within their education systems, well, they tend to show higher levels of technological innovation and workforce readiness.
So there's a real correlation there.
Yes, a direct correlation the source identifies between hands-on learning and productive capability.
And we can see this journey from that initial pencil power all the way to complex industrial production playing out in countless ways around us.
Absolutely. Look at manufacturing. You've got highly skilled technicians and engineers using their hands and specialized tools. Construction translates abstract blueprints into physical structures using manual skills. Digital platforms, even though they seem virtual, rely on the physical act of coding, designing user interfaces, building hardware interfaces with hands.
Even creative industries.
Definitely. Even in creative industries, it's often the physical act of crafting, sculpting, painting, or designing that turns pure imagination into products or art.
So across the board, it's the sustained involvement of our upper limbs as the essential tools of execution that makes it all possible.
They really are the indispensable physical interface connecting human ingenuity to the material world.
Okay, so the source wraps all this up into several powerful takeaways. What are some of the most sort of striking findings from this research?
Well, one of the most compelling arguments the source makes is that our upper limbs aren't just tools, they are the primary interface for knowledge execution. Our cognitive ideas are primarily translated into action via that sophisticated network, the brachial plexus.
Okay, so the brain leads, but the hands are the key executors.
Right. Another key finding is that motor science isn't secondary to learning. It's presented as fundamental to learning transfer. Specifically, developing fine motor control, especially in our fingers, is what builds that critical brainpage foundation. That's needed for effective learnography through activities like writing, drawing, modeling, handling tools.
And that starts incredibly early with that pencil power idea.
Precisely. The source states clearly that pencil power initiates brain page formation. That simple act is the first step in motor formatting, physically encoding abstract knowledge and literally building the neural groundwork for more complex thinking and problem solving later.
We touched on the biology earlier, the comparison between arms and legs.
Yes, and the research reinforces this by highlighting that the brachial plexus is more developed than the lumbar plexus specifically for these knowledge tasks. This biological difference helps explain our capacity for the high precision, fine dexterity, and creative potential needed in technical and creative fields.
And what about the impact on how we actually retain and use information?
That's a crucial finding. Hands-on learning leads to higher retention and innovation. The source presents evidence suggesting that practical, motor-based learning is significantly more effective at embedding knowledge deeply. It also fosters spatial reasoning and a task-driven approach, more so than purely passive instruction.
How does this bridge the gap between, say, what happens in school and what happens in the workplace?
The theory of the phases of learning transfer, as outlined by the source, directly links academics to industrial application. It actually mirrors the stages of technological development itself, showing how a hands-on educational approach can more effectively prepare students for productive roles in the economy.
And the economic implications. Are they significant?
Very much so. The research argues forcefully that economic growth depends on motor-based knowledge production. Nations that actively foster learning by doing build more capable, skilled workforces, which is presented as essential for long-term productivity and sustainability in a knowledge economy.
So, based on all this evidence and theory, what does the source say needs to change in our education systems?
Well, the final key finding is really a direct call to action. Curriculum reform is needed to activate motor knowledge. The authors are proposing a new educational paradigm, one that deliberately prioritizes motor engagement, experiential learning, and skill-based training as the path forward.
The path to making students truly technologically empowered and ready for the future.
That's the idea.
This research really forces a reevaluation of traditional schooling models, doesn't it? The source seems quite critical of systems that rely too heavily on just talking or reading.
It is, yeah. It argues that many current systems inadvertently underutilize the immense cognitive potential that's unlocked by engaging the learner's motor skills. The alternative they propose, which they call the brainpage school system, explicitly centers on the modulation of learning through action.
So, integrating motor science and physical doing right into the core of the classroom.
Exactly.
What would that actually look and feel like in practice?
Well, it means actively encouraging students to use their hands to process information. So, writing by hand, drawing diagrams, building physical models of concepts, manipulating real or simulated systems. The research suggests that this physical engagement unlocks deeper levels of understanding.
And create stronger memories, too.
Yes, far stronger, more usable memory retention compared to just listening to lectures or passively reading text.
Are there specific environments or tools that help make this happen?
The source highlights environments like miniature schools or task-based learning workspaces as being ideal settings for this kind of shift, moving from just consuming knowledge to actively producing with it. And the tools that create this essential brain-body feedback loop are varied, but they all involve the hands. The simple pencil, a stylus on a digital pad, coding interfaces, lab kits, various digital fabrication tools.
So lots of options.
Yes, they allow students to viscerally experience what knowledge transfer and innovation truly mean.
It's fundamentally shifting the role of the hand, isn't it? From just a tool of output to a tool of processing and learning itself.
Exactly. The source calls for a fundamental shift from what they term the talking classroom to the doing classroom. In this model, the upper limbs aren't just secondary aids to get things done after you've learned. They are the primary interface. They're the essential bridge between internal thought and external reality.
And this journey, from that first pencil grip to complex production, it's not just personal development.
No, it's presented not just as a personal path of skill development, but as the research argues, it's a national imperative for technological advancement and economic prosperity.
So even as automation and AI become more prevalent, this uniquely human combination of our advanced brain and our incredibly versatile hands remains central.
The source is very clear on this point. It's that unique synergy between our sophisticated cognitive abilities and the highly functional, precise capabilities of our upper limbs that they believe will continue to shape and drive the future, especially when it comes to innovation.
This research doesn't just highlight a fascinating link. It seems to provide a kind of roadmap. Based on the source's conclusions, what are the concrete steps they recommend we should be taking?
Okay, based on the source's closing recommendations, here are the key actions they propose. First, and maybe foremost, we need to actively promote hands-on learning in every single classroom, across all subjects. That means writing, sketching, building, modeling, coding, anything that engages the hands.
Make physical doing a core part of learning, not an add-on.
Right. Second, redesign educational curricula specifically to include motor-based tasks, dedicated brain-making activities, and project-based or task-based learning as central components, not optional extras.
Okay. Third, emphasize and actively encourage fine motor development, starting really early, in early education, through things like drawing, crafting, using simple tools. It builds those foundational skills. Fourth, strongly support vocational and technical education pathways that directly link academic knowledge to practical, hands-on application.
Really living that learning by doing principle.
Precisely. Fifth, foster environments that genuinely inspire learning by encouraging students to turn their abstract ideas into tangible outcomes. Sixth, create dedicated spaces, like these miniature schools or workspaces they mentioned, designed specifically for task performance, collaborative projects, and hands-on innovation.
And bringing it back to the science underpinning it all.
Finally, seventh, we need to elevate the recognition of upper limb motor science. It shouldn't be seen as a niche area, but as a core fundamental component of how knowledge is truly transferred, how creativity happens, and how problems are solved.
The ultimate goal, then, according to the research, is to empower students not just with knowledge in their heads, but with the physical tools of action in their hands. Because, as the authors frame it, the most impactful tools of the future, whether they end up being physical or digital, are first conceived and often first sketched, modeled, or built by human hands.
Wow. This deep dive into the sources you shared has really illuminated the profound and, often completely overlooked power of our upper limbs. It's not just shaping our individual capacity to learn and build skills, but how we collectively drive technological progress and economic growth.
It's quite something, isn't it? From that initial, maybe shaky grip on a crayon or pencil, all the way through the intricate movements of a skilled craftsperson or a surgeon or an engineer. Our hands and arms are this essential, indispensable bridge. They turn abstract thoughts, ideas, knowledge into concrete, tangible realities in the world.
It really does make you stop and consider how much we unconsciously rely on this connection every single day. And maybe how much more potential for understanding or problem solving or innovation might be unlocked if we more consciously engage this fundamental brain-hand loop in our own lives.
Absolutely. So here's maybe a thought for you, the listener, to carry with you after this deep dive. Take a moment, some time to just observe your own daily tasks. how much of your learning, your problem solving, your creative work actually involves your hands. And reflecting on this research we've discussed, how might intentionally integrating more physical, motor-based activity into your process potentially unlock new levels of understanding, insight, or maybe even innovation for you?